Hi again, I'm Martin Castellanos could be this, currently a first year at the University of Virginia doing research in quantum computing. I guess this is kind of the thing I do now. I make videos on quantum concepts, research, and yeah. New edition, check it out. We got this cat, I'm gonna put it right there. So I've been wanting to make some videos on some quantum research labs for a while now. Specifically, I wanted to start off with the Harvard-MIT Center for Ultra-Cold Atoms. But it turns out the research labs do a lot of stuff and it's hard to make one video on everything. The original script I had for this video had 3 different concepts I was going to explain, then 2 research papers I was going to dive into. But it was just way too much, man. Which is why I'm going to opt for this new format where I'm going to pick one concept, explain the physics behind it, and then loop it back to research being done today. I think it's going to keep the videos a lot shorter and more digestible, and then maybe in the future I can come back and do another concept or elaborate on the one I'm doing now. Although, I don't know, the Duke Quantum Center is showing me a lot of love right now. If you've been to school, which I'm assuming you have because it's kind of a legal requirement in the United States, you probably remember learning about the 3 states of matter: solid, liquid, and gas. Let's think of this on a spectrum of temperature. Left is absolute 0, and as you go more to the right, the hotter it gets. The liquid state is going to be in the middle of the spectrum, and as we increase the temperature of the atoms, they're going to start to get further apart and eventually transition into the gas state. If we do the opposite and decrease their temperature, the atoms get closer together and form a solid. I'm sure you've heard of plasma. That's going to be our 4th state of matter. If we add heat to the gas, eventually the electrons are going to escape the grasp of the nucleus. This high-energy mixture of nuclei and loose electrons is what we call the plasma state. But the focus of this video isn't high-energy states. The complete opposite, in fact. So, from the spectrum, you could say that generally, atoms get closer together the colder they are. But what does this trend imply? If we go far enough down this spectrum, what would we find?
I hurt myself today.
All particles are either bosons or fermions. For the purposes of this video, the most important difference between the two is that bosons have a whole number spin and fermions have a fractional number spin. This is Wolfgang Pauli. Besides having a sick name, in 1925 he postulated that 2 identical fermions can't occupy the same quantum state simultaneously. Okay, now I know that sounds complicated, right? But you were probably taught this without even knowing it. If you took chemistry, you might remember the orbitals of an atom. Each orbital of an atom can hold 2 electrons. But why 2 specifically? Well, electrons are fermions, so they can either have a fractional spin of 1/2 or -1/2, and each orbital is considered a quantum state. An electron with a positive spin and an electron with a negative spin aren't identical because they have different spins. So those 2 electrons can coexist in that one quantum state, or better said, that one orbital. But any 3rd electron we try to add would be identical to either the positive spin electron or the negative spin electron, so it can't exist in the orbital. This is Pauli's exclusion principle at work. The main takeaway here is that 2 identical fermions cannot occupy the same quantum state simultaneously. As long as you got that, you're good to go.
We're so cool, yeah, yeah. Yeah, we're so cool.
When we cool atoms, they start to occupy lower and lower energy states. So at absolute 0, we would expect atoms to be in their lowest possible energy state. This is where the distinction I brought up between fermions and bosons starts to matter. If we assume all these atoms are identical fermions, the Pauli exclusion principle tells us that none of them can share a state, which implies that as we approach absolute 0, these atoms are going to start filling up the states from the bottom up. This is interesting because at absolute 0 we would expect a system to have no energy, but there's an implication here that even at absolute 0, there's some energy keeping these fermions separated. In stars made up of fermions, for example, white dwarfs made up of electrons and neutron stars made up of, well, neutrons, the energy separating the fermions is what prevents them from collapsing. But in a star that's so large that gravity can overcome the energy separating the fermions, a black hole is formed. But we're not here to talk astrophysics, so forget I said all that. So we established that fermions fill in the energy states from the bottom up because of the Pauli exclusion principle, but bosons don't have the same limitation. That means that instead of filling from the bottom up, they can all exist at the lowest possible energy state simultaneously. When bosons are concentrated like this, we unlock the fifth state of matter, Bose-Einstein condensate. You can see all the atoms concentrating around the same energy state. Again, the relevant takeaway here is that you have Bose gases made up of bosons that can collapse into the same energy state and form Bose-Einstein condensate, and you have Fermi gases made up of fermions that cannot collapse into one energy state. Generally, there's ways you can get around that, but for the purpose of this video, that doesn't exist. The effects of quantum mechanics are observed on a very tiny microscopic scale, which is why you've never observed the socks in your drawers spontaneously tunnel out, and why every time you walk past a doorframe, you don't diffract into a bunch of waves. That's also why the field of quantum mechanics is relatively new, because we weren't always able to look at these microscopic scales. Turns out it's a lot easier to drop an apple and see how long it takes to hit the ground than to shoot individual electrons through a slit 300 times thinner than a strand of hair. So to observe quantum effects, we're going to want to observe microscopic systems. Ideally, we want to be able to observe the interactions between individual atoms. If only there was some technique that incorporated the stuff I just spent 5 minutes explaining into imaging systems of individual atoms. First, we create an optical lattice, and then we load a quantum gas into the lattice, and then we cool the gas, and then we focus the scattered fluorescent light from individual atoms into a camera. And that's how you do quantum gas microscopy. That's it. You can click off the video. That was quantum gas microscopy. Here's some cool details though. When you put Bose-Einstein condensate into an optical lattice where the crevices aren't too deep, it can tunnel between the crevices relatively freely. This leads to a weird effect where the individual atoms of the Bose-Einstein condensate exist over a range of crevices instead of in a single one. During this, it exhibits superfluid behaviors. This effect kind of breaks though when you make the lattices deeper, because the individual atoms of the Bose-Einstein condensate can't tunnel freely anymore, and thus the system, in the matter of a few milliseconds, transitions into a Mott insulator phase, where each atom exists in one crevice. Looking at this chart, you can see that the average atoms per site for a Bose-Einstein condensate is about 0.5, with a slight decline the further from the center of the optical lattice you go. When we transition into the Mott insulator phase, however, we can see that the position of the atoms is more well defined, with a constant average of 1 per site, followed by a steep drop off to 0. Looking at the second chart also shows us that there's a constant uncertainty associated with the position of the individual particles of the Bose-Einstein condensate. By contrast, we can see that there's a low level of uncertainty for the Mott insulator, everywhere except for this spike where we transition from full sites to empty sites. What these charts are trying to tell us is that for the Bose-Einstein condensate, where the atoms are free to tunnel, there is a constant uncertainty in where the individual atoms are. For the Mott insulator, however, there's little uncertainty in the fact that these sites hold atoms and that these don't. But there is some uncertainty in this area where we transition from full sites to empty sites, like I said. So essentially, we're controlling the probability of tunneling at a microscopic scale and imaging it. That's as quantum mechanical as you're gonna get. A microscope that uses quantum gas microscopy is called a quantum gas microscope. Very, very creative, guys. But don't get me wrong, I mean, these quantum gas microscopes, they allow us to study systems at the particle level. The applications of that are endless. For example, in the field of quantum computing, where our qubits are often single atoms, we can build a system using this technique that allows for single site readouts of individual qubits without disturbing the other ones, which is pretty important. Also, I thought this was kind of funny. An article in the Harvard Gazette refers to Marcus Grainer as an assistant professor of physics at Harvard and an affiliate of the Harvard-MIT Center for Ultra-Cold Atoms. I don't know why, but the word affiliate is so funny to me. I can picture him being interviewed and being like, whoa, wait. Don't give any credit to the Center for Ultra-Cold Atoms. They are an affiliate of mine. This was all me. Which I know didn't happen, but like, I feel like it'd be pretty funny if it did. That'd be funny, I think. Okay, well, that's it for now. I might do a follow-up video later on the Harvard-MIT CUA. We'll see. I also did leave out some things for the sake of time and as to not confuse the average person watching this video. So if you're interested in how quantum gas microscopy works on a more technical level, I'm going to link like 1 or 2 articles in the description and just read them. Really good, really interesting stuff. Yeah, that's it for now. Quantum computing. Yeah.